Right, great. So what I want to talk to you about today is uncertainty. There's one thing that's absolutely certain in all of our lives, apart from death and taxes, is uncertainty. We have to deal with it in our own individual and our own corporate experiences, whether it's our career, whether it's our finances, our romances, right, our business. We live in an uncertain world. And technology and the drive forward of technology is always hampered by failure. I think if you look at every success story, you'll find a number of failures that predated them. We're in London, and most of you will recognize this bridge. You probably won't know what its actual name is, but you will recognize it as the Wobbly Bridge. Now, the Wobbly Bridge, in actual fact, is very interesting. Why? Well, because it was closed the second day, the day after it was opened. It was opened over budget, of course, and it was closed for 2 years to fix the problem. And what was the problem? Well, it was an extremely strange problem that no one had actually thought about, right? It was something that fell out of the realms of the certainty of the age-old discipline of designing and building bridges. And it was that there was a socio-technical interaction between people that were walking on the bridge and the bridge itself. Its beautiful, elegant design actually gave it an inherent lateral sway. And that lateral sway actually made pedestrians unconsciously walk to the same rhythm. And what then happened, of course, is that there was a feedback loop which started to strengthen that sway until the bridge reached its resonant frequencies and everyone was falling about, and the place was closed for 2 years. The point is that this was something that could not be foreseen. This was something that landed in the realms of uncertainty. And in the political landscape, we're dealing with an awful lot of uncertainty and the fallout of that at the moment. Newton gave us the wonderful idea that we live in a clockwork world, that the world is deterministic. There are a number of rules which govern the development of the world and the way in which things evolve. And that was fantastic. And then at the beginning of the last century, Heisenberg absolutely shattered that view with his celebrated uncertainty principle, where he showed that in the quantum world, if we know something very precisely, the position of a particle, we know that at the expense of precision about something else, its momentum. And that then took us from a clockwork, deterministic world to one that was probabilistic and uncertain, admittedly at the quantum level. But I would argue that irrespective of our philosophical view as to whether our universe, our world, is indeed clockwork or not, if we believe it is clockwork, the thing is that we don't understand the underlying mechanisms in all of their detail to allow us to make deterministic decisions about what is going to happen in the future in the world. And we therefore have to deal with that incomplete knowledge and that uncertainty. And so today what I'm going to talk about is what my work is focused on in dealing with uncertainty, but dealing with it in a positive way, to harness it to our benefit and to the good of society and for the good of our businesses and commercial endeavors. So I just said that, all the assumptions of the Newtonian world were completely devastated because of what was being uncovered and discovered about the quantum world. And my work is really about how do we characterize the fact that there is uncertainty because our well-cherished assumptions just happen to not be true because we don't know everything to the precise level of detail that's required. Again, if we go back to bridges, we've been building bridges for millennia. Engineers have been studying bridges for hundreds of years. We understand pretty much the physics. We can model them. And yet, despite all of that, that socio-technical interaction basically shut down our London's wobbly bridge for 2 years. Now that's the bridge, a sign of a city's ambition and view of itself on the world stage. But what about cities in general? Well, it turns out that we are developing new materials for which we will build bridges, construct buildings, lay out motorways that enable traffic to move around in an efficient manner. We're developing structures through the advent of artificial intelligence. Although, for me, artificial intelligence are the tools of mathematics, statistics, and engineering. But putting all that together to define an artificial intelligence is allowing us to develop structures in a very clever way. We're constructing assets, as one you'll see shortly, through the use of robotics and robotic technologies, micro-robotic technologies. Indeed, we're about to include autonomous vehicles into our cities. We're about to use drones to start to look at how we would maintain buildings and so forth. And the thing is that we're building cities, right, with so many disruptive technologies which are all going to impinge in ways like the clockwork system that we just don't fully understand. So how do we deal with this? Well, Lord Kelvin, the great Lord Kelvin, I always talk about Lord Kelvin because he was a great physicist, but he was Baron Lord Kelvin of Largs, which is the town that I come from in Scotland. So Lord Kelvin pretty much always appears in my talks. But he said, to measure is to know. And what he was saying is that if you can measure something and you can obtain data that gives insight and information about a phenomena that you are studying or that you want to understand, that you want to exploit and control, you need to be able to measure it. So data and the explosion of data that we're experiencing today and the potential value of data is nothing new. Right? The great Victorian physicists and engineers knew the value of obtaining data. However, we really are in the midst of a seismic shift in how we can gather and collect data. We can do it extremely, almost in a costless way. How many of you are wearing Fitbits, measuring your steps so that you can check them at night? Right? Our iPhones are the amount of data that they are generating about what we do, where we go, what we eat, who we see, what photographs we take. And even if we go to engineering, good old-fashioned valves that switch the flow of some sort of fluid on and off, right? Big inert pieces of engineering structure, are now producing data. They can measure the flow of the fluid through the pipe. They can measure the forces actually on the actuators and feed that back and give intelligence and give information to those that are controlling the systems. It's absolutely fair to say that most corporations, certainly many of the ones that I work with, who are not digital born, are now realizing that their business models have to be transformed. So product-based companies are transforming to service-based companies. And why is that? Because of the explosion of data. We hear that data is the new oil, it's the new economy, and I believe it is. But let's just think about that analogy a little bit more. Data may well be the new oil, But how do we get oil? Well, we drill for it. And when we drill for that oil, what do we get? Well, we get a mixture of oil, we get a mixture of water, we get a mixture of gas, we get a mixture of shale and so forth. We get oil and we get junk. And then once we've separated the junk from the oil, we then have to process the oil to ensure that we get the products, the commercially viable, valuable products from that oil. And it's the same today with data. Data is no doubt absolutely valuable. But producing data means that we're also producing junk. Producing data means that we also have to invest in how we extract value and information from it. We are producing a lot of junk data, and in many cases, an awful lot of corporations, and in fact, a lot of scientists are unaware of that. So there are challenges as well as opportunities as far as data is concerned. So we're measuring many, many things at the moment, many more phenomena than we could ever do previously. But what should we really be measuring? What data should we really be gathering? And this is one of the questions that drives my research. If we want to tame and control and exploit uncertainty, what is the data that we need to be targeting in terms of obtaining it and exploiting it? We need to know what we don't know. I'm going to read a quote out. It's quite a garbled quote, and please don't fall asleep. Tell me how many of you recognize it. I would say it in an American accent, but my American accent's pretty terrible, so I'll stick with my Glasgow accent. The message is that there are no knowns. There are things that we know, and there are known unknowns. That is to say, there are things that we now know, we don't know. But there are also unknown unknowns. There are things that we do not know, we do not know. This was, of course, Donald Rumsfeld, and he was the butt of many well-deserved jokes, I would say, after that mouthful. But he was absolutely spot on. There are no knowns. There are only things that we know, we don't know, and things that we don't know, we don't know. The designers of the wobbly bridge, they didn't know that they didn't know about the socio-technical interaction that made pedestrians walk almost zombie-like in step to the natural frequency of the bridge. They just didn't know that. And yet we could try and safeguard that in some way. So my work and that of my team is really about understanding what and where uncertainty enters and how data, as I said, can impact this. If I look at this little thing here, this is work that we're doing with some clinicians. And in essence, we are exploiting mathematical models and assimilating data into those models, which is so the data corresponds to the images, the model you can see here. And this is allowing us to cut down and control the uncertainty that a surgeon has when he tries to cauterize the surface of the heart, right, to bring its control of its rhythms back into synchrony. And this is not a trivial thing to do, let me tell you. Now, statistics, mathematical modeling, data science has been at the center of my research since I did my PhD. And I was a late starter. I worked for 10 years in the commercial sector, before I went and did my PhD. And AT&T, the great AT&T, funded my research. And little known to me, they had actually invested in some technology that would allow them to verify, was that allow them to verify the speaker, right, at an automatic teller machine. And the problem was it just didn't work, and so they needed a willing PhD to show that in fact it didn't work, although they never told me that. So my PhD was one big failure and one big negative result. But ever since then, I have absolutely been captivated by the intersection of mathematics and statistics and engineering. Now, the one thing that a mathematician always has to be reminded is what George Box, the great statistician, said. He said that all models are wrong, but some are useful. And if we go back to our clockwork representation, if we try and model something of that clockwork where we don't know all of the mechanisms, then clearly our model is wrong. It doesn't have all of the details, but it may well be useful. And this is something my work is involved with, is trying to come up with abstractions which are mathematical or computational or statistical that we know are wrong, that are imprecise, that are uncertain, but are useful for the task at hand. So if I think of mathematics and statistics, how does this actually help? Well, let me give you an example. Some of you in here will know about the finite element method, and some of you won't. And those of you that won't will definitely have seen images like this, which basically describe a car body in little finite or triangular elements. And what it allows you to do is solve the differential equations that describe some phenomenon there. It's a triumph of modern-day mathematics. And it's transformed the way that we design cars, the way we design almost anything. And that includes in medicine with the heart example I gave you. The issue is, good old mathematicians still stick with a deterministic clockwork world where the model is absolutely correct. And the finite element method assumes that the model is correct and will give you an answer. Right? So if we were to simulate the force of impact with this car, then the finite element method would show us the crumple dynamics that would be experienced. But the reality is, there could be a number of different ways in which the crumpling could take place. Why? Because our model is imprecisely specified, because when we measure the actual force, it may not be quite exact. There may be errors associated with it. There may be some sort of distributional uncertainty. So what my work is doing is taking these approaches and converting them from deterministic to probabilistic. Now, a car is a pretty complex beast. This is Calcutta. I go there quite often because it's home of a very famous statistical institute. It's a pretty complex environment, as you can see. Probabilistic methods allow us to try and understand some of this complexity and how the transportation systems, and these are transportation systems that are absolutely creaking at the seams, work. But let me talk about digital twins. So digital twins are in essence a representation of the phenomenon that we're interested in, whether it be the car body or the traffic in Calcutta. But unlike a deterministic model, where there's a mathematical description, we take data, we take physical measurements and fold them or assimilate them into the mathematical model so that we develop over time what is basically a twin, a digital twin of the actual physical asset. And the work that was mentioned before is very exciting. We are involved with the world's first 3D printed stainless steel bridge, a pedestrian bridge, that is going to be based in Amsterdam. It's a big statement of civic pride. And our team was called in because the designers were saying, well, we're doing this really cool stuff with 3D printed steel, and we're going to build a bridge. A number of problems. The first one is that the actual material is steel, but we don't understand the properties of 3D printed steel. Is it stronger than rolled steel? Is it weaker? We don't know. The fact that the bridge is printed by robots with voids and holes in it and so forth, what the impact is going to be, we just don't know. And so they came to us to say, can you help us in some way? And so what we are doing is we are characterizing the bridge with a number of sensors, strain sensors, accelerometers, environmental sensors, and even videos so that we can assess what the random forcing of pedestrians is going to be on that structure. And we can then build, from all of that data, the digital twin that will reflect the physical structure. And it will allow us then to go to the next stage of designing and building and operating fantastic pieces or assets such as this. Okay, so a 10-foot bridge in Amsterdam has a digital twin. What would happen if a whole city had a digital twin? Now, we're asking these questions already. The government wants the UK to have its own digital twin. So, of course, for the UK to have its own digital twin, all the metropolitan areas need to have one. And so the vision that I have is that digital twinning technology will actually be scaled and developed so that we have digital twins of our infrastructure, of our social networks, of our food systems, our transportation systems, all of the complex primary and secondary and tertiary interactions that occur in a city, a complex city like London. It would allow us to model the complexities of what would happen in certain scenarios. So when policymakers decide to put a levy tax on petrol or making sure that no cars can get into the centre of London, could we have a flight simulator for London that would allow us to play forward what would happen and allow us to explore the known unknowns and do what-if analysis on the unknown unknowns? We would like to be able to test the digital city and test it to its absolute limits. And we're already starting to make progress in that respect. Modeling structures like bridges, modeling the transportation networks. We're doing work with Transport for London. As I said, modeling food networks, and also modeling the environment of the city itself. My group are actually working with the Lord Mayor's office, helping the Lord Mayor's office of London on the Clean Air Initiative. It's extremely important. But before we can manage and improve the environmental conditions of the air in London, we need to be able to monitor it. And we've got a number of air monitoring stations scattered around London. But really what we would want would to have air monitoring stations, say at every meter. Now we just can't do that. We can't replicate the clockwork system of the environment of the air in London. But what we can do is, with the incomplete data and the incomplete knowledge we have, we can use mathematical models, statistical representations to build a digital twin of the air quality and how it evolves over time and space in London. And so what you could imagine is that an individual would be able to say, well, I'm going from South Kensington to the British Library, and I want to take the route that is least polluted, especially if I'm clad in my very bright and garish lycra and cycling across the city. Then we could actually do that. Each individual could interact with the overall digital twin in an individual specific way. And this would have implications. For example, if you had to go to a hospital, what would be the best hospital to go to given the particular problem you have? My group have been working with Amazon, and the question that they are asking is, where should they put their fulfillment centers when the weather is good and everyone wants a brand new not microwave, what are they called? Barbecues. You can tell how many barbecues I have in West Hampstead. And they want to be delivered in an hour. What is the most strategic place at any point in time that they should hold stock? This is very much a problem of known unknowns, unknown unknowns, and using data to exploit uncertainty and to manage it to its best effect. So what's next? So future engineering. We want to build cities that last. We want to build cities that are constantly in beta shape, right? That will reconfigure themselves for the benefit of the population, and the population can interact with the city in meaningful ways. We're only just at the beginning of this journey. We're starting with bridges, we're starting with automobiles, we're starting with commerce, with companies like Amazon and indeed Shell. But the vision for the next 20 years is one that digital twins will tame our uncertainty, will allow us to reason about the future and about future unseen events in a much more robust and sensible way, and have cities and societies that will last and will be great for all. So the final slide. The final slide. See, this is a great example where, you know, the mighty Apple, right, still can't quite get a grip on the known unknowns and unknown unknowns. There are always technical glitches. The key here is, as in commerce, as in life, the fittest survive. We have new oil. It's going to be part of the future, the current and the future economy. Data. We have AI, which I would interpret as very clever mathematics, statistics, and engineering. And we can incorporate that so that businesses can transform themselves and be at the edge of these disruptions in the markets that we're seeing almost on an annual basis. So thanks for listening. I hope that I kept to time. I think I have, actually. Thank you.